Liu, and I'm going to tell you a little bit in a moment, has gone through, has suffered the traffic of New York, all kinds of consequences, gone through storms, hurricanes, to come here today. So this is a very special seminar. It drove down here from New Haven, Yale University, through an awful lot of traffic. Just literally came through the door about 10 minutes ago. So unrattled though, and ready to go. So thank you very much all for coming, and thank you, Professor Liu. So Dr. Chen Liu is first I want to know he is going to be my sabbatical mentor, and I'm going to be working in his laboratory at Yale University from September on. Retiring to a sabbatical. So I've got to treat him especially nice. Not that we can know.
We knew each other for a long time.
Yeah. we have known each other for a long time, and I've always treated him nice. So this won't be the first. Dr. Liu is an MD PhD. He trained in medicine and then got his PhD from the University of Pennsylvania, and then went on to be on the faculty at Rutgers University Medical School, where he was chairman of the department, and now he's at Yale University, where he's chairman of the department of pathology and Brady professor. He's probably best known for well, first of all, he's a molecular pathologist and one of the leading ones in the country. That's of course why I feel lucky to be working with him. We'll be doing work together from HSIE's laboratory. But he's also very much known for all kinds of applied biological approaches, transcending tests, establishing approaches in immunotherapies and the development of diagnostics there. And I didn't bring the right list with me, but some of his papers are cited thousands of times. So you'll be seeing his name again if you go into that field. So that's why we're really delighted that he's going to talk to us now about epigenetic drivers of liver cancer. That's something of great interest to many people in this room. The lunch is going to be in this room for convenience and for size and everything. So right after the lecture, those coming to the lunch can just stay here, and we'll take a little bit of a setup. Dr. Liu will then be meeting with students, and I think that's here too, unless that's in the boardroom upstairs. But I'll give you a tour. I think that's here as well at 4 p.m. for trainees and students and people who didn't make the schedule. So without further ado, Professor Liu, thank you.
Thank you. If you don't mind, I will. It's easier for me to speak without masks, right? But I'm fully vaccinated. I did the test yesterday. It was negative. I mean, I do it after 2 days. For convenience, because my department does have the COVID testing program. So that's okay. First of all, thank you very much the team for this kind of introduction, and it's so nice to see old friends in the team. We knew each other when I was graduate school.
Yes.
So this to me is especially meaningful and an honor to deliver this lecture at very Blumberg Institute. And when I was a graduate student at Penn, I did my thesis actually at the Fox Chase Cancer Center in Barry School. At that time, Barry is the head of the hepatitis program, and underneath him is Bill Mason, where it's for my direct mentor. I did my PhD with him, and John Tyler is just next door, and then Tom London is also next door. I would always say that's probably one of my best time, throughout. It was really great. And for Zhitao, we knew each other back to China, so it's a long time friends and collaborator. So I think this really means a lot to me to be here. And thank you very much. I think this is a really amazing place. And a little bit kind of I'm still, my head is still with the traffic noise because I left home at 6 o'clock this morning. I saw the supposed 3 hours drive. It turns out almost 5. So just all right. So I would like to to share some of our studies and in particular share some of our thoughts with you, and mean to make this kind of a presentation more informal. And if you have any question, please interrupt and move on. So this is the outline, and my talk is, basically today I would like, in terms of targeted molecular profiling, and I was first, thinking that, we have been focusing on epigenetic markers for the past decade. And, basically the first part of my talk is some basic introduction and see what are the genetic markers and how can we use this. The second part of the talk is look at the epigenetics in hepatocellular carcinoma, and to just introduce you what has been known and what have been we are working on today. And then followed by that it would be the approaches to use epigenetic data to identify novel drivers. This is really the focus of our own study. And then with that in particular focusing the early events of epigenetics, we'll show you some of the approach we have been using and how we do it. And then the other is how to integrate all these multiple epigenetic markers with transcription, and then to see that eventually, as you know, the epigenetic changes is really related to control, related in controlling gene expression. All right, so now it's just the first one. So this is very basic stuff, and as you all know, genome versus epigenome. So why we think epigenome probably more important, as we know more about the disease. So genome, you just have one. We know the DNA store all the information in the in any living organism. However, in the genome, the DNA has been organized into different chromatin, structure. And this organization really is how those genetic information is, is stored and organized and expressed in a conserved way. So with that, you can see, there will be many epigenomes for almost every cell, every liver, every organs in the organism. So that's why I'm saying, we can clearly see there's a lot more epigenome controls all the cells phenotype and all controls all the different microenvironment and especially during disease process. All right, so then the epigenome itself, in terms of how they modify it, as we know more and more, almost each day we find all different mechanisms in terms of controlling the epigenome. First off is the DNA. At the DNA level, so there's two chemical processes control the epigenome. One is the DNA methylation, and then the other is the hydroxymethylation. So this is highlighted here because this is what I'm going to talk about more about today. And then you also have the histone piece. Like when the histone organizes the chromosome, and the histone can be methylated, can be acetylated, and also phosphorylated. So all of those affect the chromatin structure, and then consequently it affects the gene transcription. And then you have the chromatin remodelers. This was recently, past a decade, I would say, there are some findings, some proteins particularly, and they will specifically affect the chromatin remodelers. And then the whole class of the non-coding RNAs, also play a role at the epigenetic level. So all of that really is basically, control the DNA accessibility. In other words, because when for the genetic information to be expressed, you must have some sort of regulatory protein to access the gene and then make the gene express. And then at the same time, you have to shut down the gene. So this is just some background information. So how, as I said, I was focusing on the DNA modification side. As you know, basically this is from the side CG sequence, and it will be a group of enzyme can methylate this C cytosine base by methylation. And then I have say past the decade, and it's really remarkable to find that this process itself is reversible. So irreversible is basically controlled by another group of genes, the T and T, group of genes. Basically, when you have the methyl group here, and this enzyme can add a hydroxy group to the methyl group, so make it a hydroxymethylation. So when the hydroxymethylation is, happens, And then what happens is that the same T1 enzyme can remove the isoform and restore the original CFG. So you can see this is a really nice thing to give at least as an opportunity to understand this like a bidirectional mechanism. Certainly, it will open opportunity for us to see how we can regulate this process and manipulate the process for therapeutic intervention. All right. So now I think I will turn to, with that background, turning to the epigenome, hepatocellular carcinoma. So why do we think that hepatocellular carcinoma? That time we believe this is really a much better model to study this epigenetic alterations. But at the same time, it's probably needed and for eventually control this disease. As you know, so you can see, this diagram just tell you, and from normal liver all the way to become hepatocellular carcinoma, which we all talk about this probably, it's a reason to cause mortality in patients' death. So the thing is, for this process, fortunately, this will be a long process to make it happen. That's one. Second is, hepatocellular carcinoma compared to many other types of cancer, at least at the etiological level. In other words, the cause of this cancer is probably much better defined than many other types of cancer, right? Because you do know what we call at least 90% of hepatocellular carcinoma, is caused by underlying chronic liver disease. Most commonly is hepatitis C and hepatitis B. Those two, liver trophic virus basically responsible for more than 50% of hepatocellular carcinoma. Then you have alcohol, right? And alcohol exposure, some other, liver toxic, conditions that all, right now is getting more attention is the fatty liver disease, and in the setting of either, metabolic derangement or after, diabetes, when you have the fatty liver disease. And then this process is also well defined from pathology's perspective. We can see the linear form transition, because the people who have this chronic liver injury eventually become cirrhotic. After the cirrhotic, the liver becomes cirrhotic, that basically reorganize the liver entirely, and then you can see in those cirrhotic nodules you actually see different degree of dysplasia. You see the cell has dysplastic changes, and then becomes earliest HCC and from progress eventually more aggressive HCC. As you know, whenever this to the terminal HCC, this disease is pretty bad one, because prognosis is poor, and up to this point there are not really good treatment options, and almost this is a very well known hepatocellular carcinoma literally resists to all the chemotherapies available. So this is why so that tells us the most important part for hepatocellular carcinoma is you have the risk population. We all know many of these people will have hepatocellular carcinoma. We just don't know when and which group. So that's how lay down the foundation to see why the rationale for us to pursue this will be how we can find really early diagnostic marker to find this early. All right. So with that, because we say that in terms of during this pathogenic pathway, in the literature there are many studies over the almost 20 years, I would say. So number of genes have been implicated in this deregulation in hepatocellular carcinoma. So kind of more really relatively well studied, it will be the TERT genes. The telomerase genes. This has been well studied. It's probably one of the common alterations in hepatocellular carcinoma. Except for p53. And so you can have like a hypermethylation or even deletion of CP CPK and 2A. So this is another very nice paper published. Imply the CPK and 2A is highly nice person. So I put this all together and just emphasize the point I just mentioned. And you have all the etiology which we know we can find out the patient. Basically, most of the chronic liver disease patients will be sort of one of those respected. And then you can see when I mentioned this, you talk about 10 to 30 years transition from normal cirrhosis to HCC. I would say most of the patients will undergo this process. So there's an important piece is the cirrhosis part. But there are few patients really they go from hepatitis all the way to HCC with the after cirrhosis process, particularly in the setting of chronic hepatitis B infection. I think this is relatively rare, but I think less than 10% most go to cirrhosis. All right. So with that, so then we decided, let's see what happened in the, we did our study first providing the first focusing the methylation part. So what we did is we select, normal control liver, cirrhotic liver, we have 135 cirrhotic liver, and also liver cancer when the patient had either resection or transplant. And then to, did this, this is the original form. This almost, you can see this is almost 80 years ago when we did it. It's using the Euthanian 450 array-based assay, but right now it's already 850, so it's much more advanced. You can pick up more genes from those. So making long story short, here we just, this has been published, so I just kind of highlight, a point here. So when we did that, we look at the underlying etiology to compare HCV infection versus alcohol infection. I mean, not infection, sorry, for alcohol disease. Okay. So you can clearly see, the epigenome changes is very different between the alcohol exposure versus HCV caused HCC. And for instance, and then you can see the alcohol in terms of the CpG island alteration is during the cirrhosis state is very low. It's about 100. However, during the cirrhosis stage without a cancer, you can see HCV, you have almost 2,000 alterations in the different CpG islands. However, from the cirrhosis transition to hepatocellular carcinoma, so all of a sudden you find that the magnitude of changes from, you see the yellow circle from 107 to 25,000. So basically, there is a acceleration process from, from cirrhosis to HCC with alcohol etiology. But with HCV etiology, you also have acceleration, but the acceleration is relative because the baseline is very high for HCV infection. So, and then, however, if you look at the cancer itself, really they are comparable. There's all 20,000 alterations, and most of them to really overlapping. So this tells us, I think, at the time of the HCC, when they become a cancer, they are very similar because of the underlying etiology will be less important. However, during the stage from normal to cirrhosis, from cirrhosis to cancer, there's big difference. So this is also, for us to, pay attention is when we design the biomarkers, that maybe we should think about, the underlying etiology, so which markers to focus on. And also, so this is basically the landscape. We started this. Now the question is, those are the passengers or drivers? Because for us, we're always thinking about where we can find the drivers, right? That's the holy grail for cancer. So then we just, move on to the next step. We decide to see how we can find driver events instead of passenger. So to find the driver, as you recall the earlier slides I showed you, there is a process. If you even look at the tissue from normal liver to cirrhosis, And in cirrhosis, you have the dysplastic nodules, right? The dysplasia process. So from those dysplasia process, and eventually become cancer. So I think in order to really define what is the driver event, you need to look at the early process. As I mentioned, you'll see when they reach to the end stage, they are pretty much really adopt the real cancer phenotype that regardless what's the underlying etiology. So what we decided to do, we wanted to see if we can start analyzing the nodules in the cirrhotic liver. So basically, there are so many nodules in the receiver outward. So this is what we did, what our approach is. We have the patients being, undergoing explant. Sometimes the explant liver is a target cirrhosis. We just cut all those slice different pieces and start analyze each individual nodules. We isolate those individual nodules and look at pathologically, usually look at the pathology, and then do the methylation array and to detect what's happening. And then use those information constitute this phylogenetic trait. So this is a kind of diagram, you can see we have generate, and then to classify what are the different nodules. But one thing I can tell you from this study, this is really for our pathologists, we all say cirrhotic liver, they are all similar. But actually at the molecular level, what we find out, each nodule is actually molecular. They are very different at the molecular level, at least look at the DNA methylation profile. And then, certainly the most important question is how to get a meaning out of this, how to actually say this is the, how to really interpret the data, how to, use the information. So then we, use, borrow from really the epigenetics, right? Look at the, borrow the idea from people doing evolution, and then look at the genetic trait. So we cover the epigenetic, epigenetic, we call the epigenetic progress score, so the epi score. So basically, it's coming with a defined certain system. You compare, classify the normal and with cancer, and then you look at the score. Basically, the score, the number of score is proportional to how far, how close they are to the hepatocellular carcinoma. In other words, the higher the score, that means they're more leaving from the normal liver mold to the carcinogenic pathway, mold walls and cancer. Right. This is, and then histologically, because really there is not many good markers really know good histological marker or pathology marker to define the cancer in general. So basically, we use the Ki67. This is basically is a marker to against the PCNA. The PCNA, as you know, it's a marker for cell cycle, right? So use this Ki67 skinny score. It just on the assume the cancer will have a high proliferation index, right? This is basically what is our assumption. But I there's a limitation. Proliferating itself does not directly equate to cancer, but it's related to cancer, right? So we use this Ki67 index compare our IP score. I think we do find a very good correlation, and so that means so the Ki67 score is higher, then it's more likely the epigenetic score will be higher. So I think using this approach, then we start to see building the score and then to find out what are the potential candidate genes may be the driver. So how to classify that? This is basically how we use this IP score and also look at all the bioinformatic analysis. This is how really contributed to this great postdoc, like Ram Tilady. So he used to be he did a PhD in biochemistry, and then he developed himself into a bioinformatic person. So he basically did all this analysis. It's amazing. So Keith Robertson and I supervise him, but we don't, we will have limited knowledge about how to building this thing. Basically, Ryan has been looking all of this analysis. I mean, long story short, that's, you see this, from normal, all this, this technology, all the carcinoma. At the end, we identify those kind of what we call cluster of, leading genes potentially, can play, we'll say a pool of potential driver genes. It's 300 plus genes. And then we do the, run the correlation analysis using TCGA data as well, and to cluster, to find what's their findings in terms of estimation. And then, also look at, their expression level, the underlying gene expression level, and also methylation level. Anyway, so we did identify this particular thing, FMO3. So it is FMO3 is really oxidative, involved metabolism of phenobiotics. So what this gene does, this kind of surprise is highly methylated in hepatocellular carcinoma and also in the early dysplasia. So what is FMO3? So the FMO3 is actually chemically is highly expressed in liver. All right, this is a very liver specific gene. So this gene was a function, it's real function. And I mean, not many studies, but I think based on what I work in the literature, it looks like this gene is responsible to convert trimethylamine, the trimethylamine, the TMA, is the chemical we smell when the fish is rotten, right? Because when you have rotten fish, you smell that kind of fishy stuff. That's actually TMA, the trimethylamine. And then apparently in human, we in the GI tract, there are so many bacteria. So the bacteria will produce a lot of TMA, but none of us walk around with like a lot of fish, right? Because it's weird. The reason for that, because the liver has that, because all the TMA travels through the portal tract system, get into liver and be metabolized. So that's the common result. So there are about 20 cases report, with genetic deletion of this FMO3, like a genetic disease, the babies without FMO3. Indeed, according to, as I said, 20 so far reported. So for those babies, the only phenotype so far known is really the baby has high levels of TMA, so the baby will smell bad. Right, this is a kind of a finding. And then, also, I tried, all the way the literature in 1960s. So there was a very short paper, one-page paper in New England Journal of Medicine. So what they published is, so people with cirrhosis, with advanced cirrhosis, will smell bad because they didn't define what the smell bad, and they will have higher levels of TMA. That was just that paper back then. That's it. So I think this is a really fascinating, to identify. This is really our top target. So now that's where we are. So because we got this gene, so we certainly have to show you. We certainly will focus in looking at this gene to see what is the significance of this gene in terms of carcinogenesis. And also, so we just got the knockout mice. Now we have the liver specific knockout of FMO3, and then so preliminary study indicated those mice, the life expectancy seems okay for the mice, but there's no lethality in the early stage. But however, if we expose these mice with alcohol, so those mice seems to suffer slow damage. So this is so far, we certainly want to look at that. And then the other what we like to see if FMO3 can be as some markers, look at. So this is just interesting. And then with similar kind of methodology, so we also look at, the identify other things, EZH2. So this is actually enzyme involved and to we call it the histone readers, basically the H3K27. So it's the gene regression is also function, similar function. So we haven't looked at this carefully yet, but it's another gene. All right, so this is so far, high leading this way, then we can see to further look at how those epigenetic markers really meaningful at the transcription level. So far, we have seen just observation, it's a correlated study. And then, we then decided that let's focus in a few of those, cases, and then to do not only just the DNA methylation study, also look at the histone modification, and also the mRNA expression. So basically, look at the mRNA expression, transcription, methylation, histone modification, and then see if the correlation there, we call it the integrated approach to identify, the drivers. Anyway, so with this study, we compare, certainly compare the normal versus cirrhosis, and then cirrhosis versus cancer. And many genes we classify them, clearly, and as you know, whenever you do it, you can always classify this, different cluster, and then you look at the genes, you have, the genes probably related to apoptosis, migrations, and all the proliferations. And then I want to focus to like the graph here. You can see. So what happened is, interesting part I mentioned. Remember, the other thing is really the bidirectional changes, because now I know there is a technical challenges to look at the hydroxy methylation, but I think we started looking at that because that's probably more meaningful as well. You see the methylation, you look at the normal cirrhosis, you look at the total methylation is based on mass spec. So there are changes, there you have, alterations, and not as striking as the hydroxy methylation. Because if you look at the hydroxy methylation side, so that's the thing is getting the methylation reverse. So from this here, you can clearly see the ability for the cells will be able to continue to do the hydroxy methylation is so critical, because that's the one to actually erase methylation and turn the gene back on. So that means you do have this other feedback system to regulate the cells. I think that system, at least from this, from our data, clearly more compromised than the methylation. Right? Does that make sense? You see, from normal, you have very, robust the hydroxy methylation, machine working itself. But however, in both cirrhosis and CC, severely compromised. So as I said, I think this is from this we feel later for us to really thinking about the identify the underlying event, probably focusing hydroxy methylation probably more fun. But at the same time, I say in terms of technically, the doing hydroxy methylation certainly more challenging than methylation, right? So as technology improves, yes, please.
Yeah, so oxy methylation really is a process to remove the methylation. So here, kind of opposite to operate that function, have the reusable process of removing the methylation while the still see the methylation goes down to high.
Yeah, see, this is a good question, but the thing is, what the point is always, it's just not, see, even the hydroxy methylation, this is the amazing part. I would say it's also the more complex part. Because when the hydroxy methylation go to do this, to add the hydroxy group to the methyl group, nobody knows how they do it. Because certainly it's not randomly, just again, for example, even we express a tag 2, tag 1, expressively. What you find out, they do not add hydroxy group to all the methylation. So apparently there is something they selectively remove it. Because this is also counterpart, true. For cancer overall, if you look at the cancer, see the overall methylation process, you look at this is clear see, it's low. You look at cancer, they are generally hypomethylated. However, if you look at some genes, as the one I just mentioned as a FMS3, So certain genes are hypermethylated, but in overall, this hypermethylated.
But the hydroxymethylation is transient, right? I mean, it's dehydroxylated and then returns to
Yeah.
cytidine.
Yeah.
So that would be why it kind of disappears.
I mean, all of those are transient.
Yeah.
So even the methyl, the methylation, because when I first looking into this, I saw the methylation would be the adult start, but it certainly is not. Yeah.
Yeah, my understanding is that the hydromethylating, that liquids just reduce the dynamics.
Yeah.
Right. So basically, the methylation events also reduce.
Yeah. Overall methylation reduced.
Yeah.
However, certain genes are
Yeah.
lower than others.
They reduce the dynamics.
Yeah. Yeah. Exactly. Yeah. Okay. All right. Then we also look at the histone markers deregulation. As I said, we have these 10 cases and trying to correlate and at the histone level and compare the gene expression level. The histone level to the chip acid and look at the four main histone modifiers. And then use this data, then just classify through the correlation and again, particularly look at follow that point. I mean, this keep jumping. Follow that point is really that you can see indeed the overall hydroxymethylation activity is done inside the cell. However, in the certain area, particularly we pull out all the enhancers, right? You see the enhancer. As the enhancer, as you know, is the main transcription regulator. At that level, the hydroxymethylation actually quite active. So this is how we see. So far we don't understand how that system, how the cells will know. I mean, certain area, those the term, tag, in that will either hydroxy group to log genes. So this is really the part still ongoing. And then with this data, put all of them together. As I said, it did identify it's correlated very well with FMO3 I already mentioned. And then the other gene, we also, from this approach, also identify another one, is the LCAT. This is another lysine cholesterol acetyltransferase, LCT. This is also related liver specific. So up to this point, through all our findings, we find all the alterations occurs for some of the enzymes, right? So as you know, the liver is physiologically is a metabolic organ. So far as all these metabolic related enzymes are altered. So this is really, it's interesting, but at this point we don't have explanation. And then put it all together and then just show you, as I mentioned, we have this FMO3 correlate very well. The other one is another enzyme. It's called, it's a COMT. So this is the enzyme actually responsible to transfer methyl group from SAM to catecholamine. So this enzyme expressed not entirely liver specific, but somehow it's highly expressed in liver and also in the brain, in the neuron and all nucleated red blood cells. Those are the chemical expression profile for COMT. So for this COMT, we also feel this is very little is known about the function of this gene. So we also generated this COMT knockout mice, and then right now see to determine phenotype and to see what's the correlation. And then, all right,
The methylation level is in the promoter region.
yeah, in the promoter, yeah. But I mean, when we will have the data, as you do the arrays, it's all over the place. We just pull the promoter region to analyze.
Yeah, that's a very nice correlation.
Mm-hmm. Yeah. And then, did some cell experiments just to make a point to see so far of all our liver cancer cell line, we have a dozen. All the liver cancer cell line, they do not have expression of IMO3, they do not have expression of COMT. this is a really very striking. You know, you I mean, any cells you have, you look at F1C, they're out there, right? They are. So we believe, you know, look at the promoter reason, we believe they are highly methylated. And then the question we have is just see if we can exogenously overexpress F1C and the COMT. So far, it looks like overall, when you overexpress this gene, you actually negatively affect the cell growth. I think, you know, this is a really, I would say, it's very, you know, rough, you know, experiment. I don't know how much we should, rely on this, but I think it's phenomenal. Certainly, we're doing more analysis, more carefully at the single cell level. Right now, you know, Ibo, who is another postdoc, just joined us. So he's going to define this more carefully to look at the true function of the atmosphere and the content system. Okay, so with all that, I think I heard you know, the wheel a little bit, and then we say with all the finding, as I said, we cannot look at liver tissue all the time, right? Because all of this knowledge we would like to do is to see if we can develop a serial blood marker, you know, based on the perfect blood. So that's how, you know, we're thinking about the circulating methylated DNA, you know, so as a detection marker. So I throw this slide here because, you know, this is a part of my, you know, my sort of clinical type of work. So I participated in this particular trial, and I was the site PI at Rutgers. So this is a circulating methylated DNA for colon cancer. So they focus on this using the SEPT9 gene. So the idea is this test will be able to, as a substitute, you know, as an alternative or substitute for colonoscopy. As you know, right now, people, when they are older than 50 years old, they are recommended to do colonoscopy. But you know, that procedure may not be, somebody done that would know that it's not that pleasant. In a way, some people may say they like other alternatives. So this is the trial actually for that purpose. Say people refuse to do colonoscopy and then using this feedback, you know, use this marker. So what I'm saying that is because this is exactly what I like to find something in liver cancer as well. You know, in this one, I mean, it's very clear cut. This is a very good marker. It's a SEPT9 for liver for colon cancer. It's very straightforward. You know, I'll show you the data. So then, you know, as I said, while we do all of the tissue study, you know, focusing on those drivers. And then, you know, if you look at the literature, there are a number of papers in over the years has been trying to say, wait, you know, I want to go all of them. You can see a number of genes has been considered or been tested in their particular experimental system. Look at the DNA methylation to see how the epigenetic modified DNA in the blood can be used as a surrogate marker for HCC detection. And then, you know, this was another paper, this is a recent one published. You know, they had, I think they have one of the larger, you know, data sets to compare. So they ended up using the real approach, look at the circulated, you know, in this case, they actually look at the mutation rather than particular methylation. And then, you know, use that approach, certainly they will be able to differentiate, you know, non-HCC versus HCC. And then, you know, this is, you know, another paper also, you know, from this school. So they have a very large data set as well, have 1,000 cases. So in their case, they use a group of a panel of methylated marker and to differentiate, you know, try to differentiate HCC versus. So with that, I think it just gives us more confidence in say, okay, potentially it's doable, and you know, other group has, you know, have demonstrated some of the validity of this study. So then, you know, and we will use, you know, started to look at, you know, using, you know, we have all, we're thinking about thousands of the data we obtained from the tissue, and some of them we have the, you know, peripheral blood, and then we started look at the DNA methylation profile of the peripheral blood, and to see what's the correlation between the blood marker and the cirrhosis. So, you know, long story short, you can see, you know, this validated discovery phase. But I have to say, you know, from this study, we find the tissue, the tissue micro, like basically the target genes, actually we have 300 of those genes we classify. And trying to correlate with the peripheral blood, it seems like the correlation is not as good, right? That's just basically the conclusion right now. Has some correlation, but not very good. So basically, similarly, and you use the primary tissue, and even you look at the TCGA data, and try to analyze that, and the circulating free DNA marker and the tissue marker, there's big discrepancy. So this is really kind of disappointing to us, but I think that it's just we saw that all the tissues directly move on to get in the blood. So this will certainly give us a lesson, we say maybe the discovery phase should be focusing on the blood, to identify the marker, not entire, tissue could be a reference. So that's what we are doing right now. So we are collecting clear HCC patients, their blood, and the cirrhosis non-HCC patient blood, and then to use those blood to do what we have been doing with the tissue, and then to do that again, because I think the hypothesis is we may have better yield for a liquid biopsy marker, because we're talking about CD2 human approach. The tissue part allows us to identify those genes and to move on to look at the mechanisms, and to apply that to to clinical, as I said, the holy grail is to find the liquid biopsy marker.
That's actually very interesting. Indicates the circulation, those change does not necessarily come from diseased tissue.
Yeah, you can explain that way, but that's a possibility. But somehow, the liver is almost like blood organ, the blood circulating there all the time. But there must be a source of liver from there, right? But
of course, when you say that in the tissue, you see a different profile from the
blood, yeah. But then the question is always, we don't know whether the tissue, you have all the mixture in the tissue, so what kind of things.
So in the tissue, you always pick up very small portion.
Yeah, exactly. Yeah. The blood is a mixture, wash out, wash the liver every minute, so then we wash out some. But I think this is what our pursuing right now is to use the plasma to
when you do this precancerous nodule, you say you dissect a lot of these different nodules.
Yeah.
So among the nodules, how big is the difference?
Oh, this is very significant. I showed you see that it's very different. But they share some, similarity, certainly. But it's, you compare nodule to nodule. That's why I'm saying this heterogeneity. Even the nodule, as you know, because even as a nodule itself, there is cluster. Almost 1 million cells in that nodule, right? Three-dimensionally, those nodules. But I think even from cell to cell, maybe also different.
Yeah. So that's actually make your work like those follow genetic or follow epigenetic, those kind of things even more difficult, because every time you pick up a very small portion from this patient, from that, right?
Yeah. I agree. So that's just at some point. The IP, the IP score, it's just composite score. Somehow it's a summary of that in the class. It's more like a higher level thing. If you drill down, I think this is another area you probably know. So I think we just started, with recruiting new faculty to the department. So they invent the technology, the spatial transcriptome. So basically, they look at that single cell level on the slide, look at the transcript microarray at single cell level. So then they thinking they can adapt, sort of to extend that technology, look at the methylation at the single cell level. That's where, the only way to solve that, you mentioned would be, at the single cell level.
Yeah.
But when you do the single cell sequencing, we have done that. It doesn't help us too much because we know they're different. Yeah. Because then the thing you lose the spatial interaction. You still know that's up to this point. We all have to pull the tissue or blood all together. But I think that to really have this result is look at keep the spatial, keep the tissue context, and then look at those different cells, what's their methylation genetics. I think it's a challenging, but I think that we are going to collaborate on one. They just published the cell paper a few months ago. It's a spatial transcriptome. It's very complicated.
So just comments that actually when we study HBV pathogenesis, that's also the similar things because of heterogeneity of the hepatocytes. So that's exactly just like you study HCC.
Yeah, I can. So it's outside. I can even show you the really histology finding. For example, if a HCC surrounding nodule, they are same patient. You look at the nodule. Some nodule is 100% HPV surface antigen positive, 100%. Whenever a nodule is positive, the entire cells are positive. Then you look at the nodule adjacent to that, absolutely. You see, this is like you won't be able to see it. You lose the spatial, relationship. I mean, that by itself is something. So it's funny. I think that part I try to work with Bill. So Bill was trying to do macro dissection.
With Woodchuck, I think that we published.
Yeah, he published all the time. But the human part, piece I showed him as well. I said, look, this nodule. So Bill has been testing the theory about the adaptation because I always think there will be the liver will have the group of cells become resistant to the infection. So that's all right. So this is what we're doing now. So in either case, I think that it just to show you here the other ways, more on the practical side, is look at this. Is what I mentioned about the cycle-9, because we have to adapt something more clinically useful technology. In this case, I show you two. It's the parasequencing. This we do parasequencing from peripheral blood to look at this. First use the cycle-9. So it's correlated, very well, basically like static measures to show you. And then also develop the digital PCR approach, for the cycle-9, and I mentioned for the colon cancer. But I have to say, interesting enough, I have collaborated in France. So he has tested about 500 HCC serum. He also finds that cycle-9 could be a surrogate marker for HCC, all right? So he actually published that paper. So we are collaborating on that. But I never saw that the cycle-9 would also have a role in HCC. But so far, I have to say, there is a phenomenon, so this is one area I think the GTAL team can figure it out. Normal tissue, no cycle methylation, right? 0%. HU8, A235. So this is a primary hepatocyte we generate. In our lab, we tend to do culture primary hepatocyte. This is primary hepatocyte, right off the normal liver, 0. And the HCT116, this is colon cancer cell line. So the colon cancer cell line, you look at the methylation, 93%. We know this is all known. However, the HCO2, this is a cell line we derived from HCC patient, right? So the HCC patient has a history of hepatitis C infection. At the time of transplant, the HCV was negative, and then we grow a cell line we call it HCO2. This is a new cell in the new cell line in our lab. So this cell line is almost resistant to all the things compared to, let's say, HG2 cells or HUS7 cells we probably use. This cell line has very high propensity to phenotype. So I think that even for cycle-9, you look at 87% methylation. This is I just say, I welcome everybody trying to, if you want to do something, you can look at the cell line. I will share the cell line with you, can do something. But I think this is a very distinctive cell line. That's what I know it. I think I sent it to GTAL, try to see if they work with hepatitis B something.
Yeah. I remember we put this CP.
Yeah, so this is very unique cell line. You can see this shows that even the cycle-9 are now supposed to be in this, liver. Okay, then similar approach. So we, went ahead and trying to develop the same assay using the FMO3 I mentioned. There was this parallel sequencing and and also digital PCR trying to develop the assay. So far, focusing on cell line, and then we'll see what happens in the virtual lab. So this is basically, sort of put all this things together. This is kind of what we have been doing, where we're going to go, and then, as I said, the future for this is the cfDNA. So because this is a really clinical problem we have to deal with, because there are fewer and fewer HCC biopsy, because radiology is very good to pick up some of the tumor, and for pathological diagnosis, it's more to monitor. So I think I hope my time. Okay, I have 3 minutes. I just very quickly to tell you another story coming from the epigenomic study. So this is the HCV versus HCC rates, because as you know, there is miracle drug to cure HCV, HCV infection, right? This direct antiviral agent. So now the question is always, when you get eliminated the HCV, can you also eliminate the HCC or liver cancer risk? That's certainly the question, right? Because you get rid of the virus, but whether the cancer risk is still there. I mean, those papers, it's still controversy, a little bit in the liver. Some say you eliminate the virus, you eliminate the cancer risk. Some say no, the cancer risk remains. This is the paper I just quoted here. And then we decided to look at, see how HCV exposure would cause any methylation changes, and whether those methylation changes can be reversible, right? Because the thing is, so this is basically a very nice system. I just, won't go through, this is the HCV replication. You have very positive, then you look at the epigenetic, DNA methylation changes, and then you use the, the DD, the direct antiviral drug eliminated virus can be, 100% eliminated, and then to analyze again. So make a long story short, because I know we run out of time. I think we just even this paper just show up in April pathology, so you can look into it. So the bottom line is, so we believe the HCV infection by itself actually causing the DNA methylation changes, and those changes can be permanent. In other words, you remove the virus, and those changes still there. So we coined the term called epigenetic scar. So basically, you have constant virus into it, causing the scar remain. I mean, this, and then with further analysis, interestingly enough, what all the scars, so far our study seems to suggest the HCV infection causing the methylation changes is the scar most happened at the innate immune response genes, like interferon response genes. Group of interferon related genes be methylated almost permanently, even if you get rid of the virus, those still remain. So this is that's the sort of the conclusion of that paper. So now certainly we'll go into more details about those genes. But in a way, there's another mechanism where you think about the virus trying to survive, and they try to inactivate innate immune response as whatever they can do. So this is but then also by extension, we would like to see if this is the only HCV sort of virus specific, or this could be a more broader or generic viral altered genomic change. So this is certainly, to our surprise, this is a really a nice observation. I think that, this, as I said, in April. All right, so I think that I will kind of summarize what I have done. Just to say we do believe this could be an approach to define or dissecting the intratumor heterogeneity. Epigenetically, we clearly see the heterogeneity. So we do believe also integrating multiple omics approach, it is possible to identify potential driver event and to create the 12 markers, right? And then also the last thing we want to, certainly those putative, driver genes as a, my talk, we identify those candidates. Certainly will create new research opportunity and new research direction. And for, I guess that now the student and postdoc will have work to do, right? And just focusing on those three to find out what their role, in cancer, and more importantly, to see any of those genes can be finally being translated into, some clinical use marker. So this is the part of, working with, team and, say, we had a phone call together, talking about, you guys may have some target gene. Certainly this would be the interface. We have a lot of, actually, yesterday I had a conversation with Dr. Kumar at the VA hospital. So she has collected several hundred, patient cohorts with all the sort of serum, tissue, and which HCC in the veteran population. So they have a multi-center grant, 47 centers, clinical trial, basically define every liver cancer cirrhosis patient. They will follow them longitudinally for 7 years down the road. So grant just came, I think, last week or something, so that's why we got together. So I think this is really exciting to have all this put together. Maybe hopefully we can get something done. So this is one. The last point, this is also interesting because based on the, so I think it's HCV, maybe other viruses, they can actually create this epigenetic scar for long-term exposure. Oh, I stopped, I stopped there, and I think I have to say, Keith Robertson and I have been partners for 15 years already. So we both started career at the University of Florida. So he is a biochemist. So he moved on and he went to Mayo Clinic. So I moved to New Jersey and now New Haven. So our lab is very actively engaged together. So we have live meeting together. So now the the Zoom make it all available. And then I think that also particularly I would say that most of the work as is done by EPO and ISIS Luna, and that in case lab. So basically they run related. So he's the one basically kind of putting all those data together. But we have produced all the data, but at the end of the day, we need a grant to put all of it together. So this he's played a pivotal role for our program. The great thing is that he will continue. I tried to hire him to New Haven, but he decided to go back to the US. So the good news is that he will continue to stay with Keith, in Keith's lab, stay there. So we can name it. Thank you very much for your attention. Really
We'll take a few questions with everyone present, and then if people want to leave, we'll stick around. And I think the lunch is here, but Pat, you had your hands up first.
So, this is kind of a general question. Hepatitis are highly mandatory. So there must be a lot of epigenetic DNA modification that goes on in normal liver cells.
Yes.
So are you saying, or am I taking away that downregulation in that methylation is a driver for cancer?
That's a great point. We don't. The answer is I don't know, but actually we pay a lot of attention. As you know, it's clearly an age-related phenomenon. When the liver gets older and older, they will have more, like a burn. That's a clear cut. So we don't know at what state what that turns on and what drives it. Almost for sure there has to be some histone, the process phenomenon. Great question. I think there's, my graduate student at ISIS, actually, she's looking, all the epigenetic data and actually just try to correlate with the aging effect. Look at the concept of epigenetic clock for aging. So clearly, so right now, she presented this at the AACR meeting as a poster. So clearly, we find that it's the HC. Put this way, if you look at the clock, if the normal liver, let's say it's it's 30 years old, the cirrhotic liver is about 70 years old. The liver cancer is reached almost 180 years old. So this is based on the epigenetic clock, the same, what I mean, the same age group, I say also. So clearly there's aging process, affect it. Lots to do, but just don't know. Thanks.
Sue and then Lou.
Yeah.
I mean, great talk, very comprehensive. It's a little bit like yeah, I think that somehow for the tissue that didn't translate to blood in terms of biomarker. But yeah, few blood tests out there, I'm sure you are aware that exact science, they have few that they only use like 0.45. And have you ever tested their markers? Because they are blood markers, they are methylation markers.
Yeah.
And
Yeah, that's what we are doing, trying to do. As I mentioned, this 2-hour surprise, I think probably why, because, the serum, to be honest, you think serum is more readily available, right? Because it's easy to be available. However, if you do study, particular original study, it's very hard to get a very annotated to the serum data. Usually the sample, I can easily give you the liver tissue without the clinical indication because those are very well-defined patients. But serum sometimes is hard because clinically you don't know how you identify those early HCCs or later HCCs. And plus logistically, I think it's very hard. I mean, to put this way, there is a logistic hurdle in terms of using blood because it's harder to control too. But that's why, 2-hour surprise is, as I said, disappointment as well, because I say, you have all the tissue marker, translate to serum. That's clearly shows the other way. We published it, we could actually generate some splash. Then a lot of people say, yeah, we noticed that too. Not only this, some other things. It's always surprising. But
so I guess I probably missed it. So the data you have is from serum, not from plasma.
Oh, plasma. I would say I should be plasma. Yeah, we usually do plasma, but now serum.
Lou, did you have a question? Yeah. And then we'll break. Go ahead.
So I have 2 questions.
Yeah.
One is you identified several driver genes that are hypermethylated. Have you focused on any of the hypermethylated, such as amyloid?
No, I haven't.
The second question is, it looks to me the hydroxyl methylation is nicely correlated with the HCC progression. Is it possible to try to correct the PET function? Maybe deliver some extra amount of PET to improve the suppression of the five method.
That's good point. This is what everybody is talking about. Say, if you can control the hydroxyl group, you basically create an opportunity for changing the genome in expression. Right now, the only thing, as I said, is the tag proteins. Tag protein expression. We know it's actually very variable on different diseases, different stage of disease, right? Certainly, how you're going to express, use tag, modify tag to let the tag to play a role in terms of hydroxymethylation. That's really the challenge because, as I said, we just cannot control specific. Yeah, you put the tag in, yes, you will add the more hydroxymethylation activity, but doesn't mean you will be able to specify the genes. I think this is really the challenge.
What I recommend now is let's just thank Professor Liu, and we'll stick around a little bit. If you have questions, come right up. We'll let everyone go, and we'll be able to take questions. And then, of course, you may be meeting individually with Professor Liu. And then later, the trainees, I guess trainees will be here at 4, and I think lunch is here. But thank you very, very much. So if you have questions, please just come on up and stick around. I'm going to go check on the lunch, and I've saved my questions for lunch.
Yeah.
Thank you.
Yes.
Thank you. All right, I'll be right back. Make sure.